Okay, let's try an example here. So here we have to determine the coordinates, an exact value. So we're not going to give a decimal approximation. We're going to give an exact value of a point P on the terminal arm with an angle in standard position. So an angle of standard position of 25 degrees on a unit circle. So if this is key as well, if we have some unit circle, what that means is that the radius of that circle is just 1 unit in length. So that's what we mean by a unit circle. A unit circle is a circle of radius 1, and the center of that circle is at the origin. So there's a unit circle. Hey, if we draw some line from the center to some point on the boundary of that circle, that would be of length r, which for a unit circle is 1. So the radius is 1 for a unit circle. Okay, so determine the coordinates and exact value of point P on the terminal arm with an angle of 25 degrees. So we can draw 25 degrees. 25 degrees is roughly here. What's the associated terminal arm? The associated terminal arm will be something like that. So this terminal arm, in principle, really goes forever, right? But again, in particular, we have a point P on this terminal arm. So here we have a point P on this terminal arm. And this particular point, I'm really bad at drawing circles. This particular point has coordinates. Right? So this particular point, it is on the terminal arm that is associated with a 25-degree rotation for an angle in standard position. And from this, we could actually, if we zoom in, why not? If we zoom in, is that the maximum? There we go. If we zoom in, we could even make a right triangle out of this. And we can notice that this particular right triangle, it has a hypotenuse of 1, of length 1, because this point P lies on the unit circle. So it has a length from the center to the boundary of 1. It has a height of y units, and it has a length of x units. So what can we do to determine the coordinates of point P? Well, let's start with x first. If we want to first determine the x coordinate, well, one thing we have is the fact that r is 1, and we're looking for x. So, and we have the angle, obviously. We have the angle. So which one of these ratios could we use, right? If we have the angle and the radius and we're looking for x, well, we're not going to use sine because sine would, we have the angle and we have the r value, but sine would help us look for y, so we'll actually use that later. We're not going to use tangent because for tangent, we actually have 2 missing quantities for the tangent ratio. So let's use cosine, right? Cosine, we have the angle, we have the r value, and we're looking for the x value. So let's use cosine. So we can say cosine theta is really just the ratio of x over r for some angle in standard position. And we want to solve for x, so multiply both sides by r. So x is equal to r cos theta. Plug in all your numbers. So r is 1, theta is 25. So x equals 1 times cosine of 25 degrees. And if you type this into your calculator, you're going to get a decimal result. And so for an exact value, we can just leave it like this. For an exact value, we can just say x is cosine of 25 degrees. There you go. All right, so we found the x coordinate. It doesn't look like a beautiful number, but there it is. It'll be a number relatively close to 1, more than 0.5, anyways. So let's look for the y coordinate now. So we have the x coordinate, right? So for our point that has x and y coordinates on this terminal arm, we know that the x coordinate is cosine of 25. And here's the question: what is the y coordinate? What is the y coordinate? All right, so what is the y coordinate at this point? Well, again, like I said, when we were searching for what ratio to use for the previous example, we will be using sine here, right? Because sine, the sine ratio, uses theta. We'll need to know r. And if we have theta and r, we'll be able to look for the y-coordinate. Okay, so sine of theta. So in other words, sine of theta has the right mixture of what we know and what we're looking for. Right? We know theta, we know r, we're looking for y. Okay, so to find y, we can just multiply both sides by r. So we're solving for y here. R times sine of theta. You might be able to see where this is going. So here, y equals r, which is a length of 1 because it's on the unit circle, and times sine of 25, right? Because 25 degrees is the angle theta. Simplifying here, a trivial simplification, 1 times sine of 25 is just sine of 25. And we could type this into our calculator and we would get some sort of very long, ugly result. Less than 1, greater than 0. But in any case, this would be the exact value, and we can't really write it any differently than that. So sine of 25 degrees, that's the y-coordinate. So what are the coordinates for some point P on the terminal arm of an angle of 25 degrees if point P also lies on the unit circle? Well, the x-coordinate of that point is cosine of 25. The y-coordinate of that point is sine of 25. And this is your answer. Now, this is something that we can actually generalize for unit circles. So this bears emphasis. So for any point, with x and y coordinates on the terminal arm of angle theta in standard position, if P also lands on the unit circle, it's a very important constraint here, it must be also on the unit circle, then the coordinates for point P are the sine and cosine, or the cosine and sine of that particular angle. So we noticed that for an angle of 25 degrees in standard position, if we have some point P on the associated terminal arm, and that point also lies on the unit circle of radius 1, then the x and y coordinates of that particular point are just going to be the cosine of that angle in standard position and the sine of that angle in standard position. This is generally true. So if you have some point that lies on the terminal arm of some angle theta, and that point is also lying on the unit circle, then this will always be true. And this is something that allows us to greatly analyze in a very efficient and simple and elegant way the sine and cosine functions as well, and to be able to find the graphs for them relatively simply. So this is actually a really, really important relationship, and it's so important that I will actually end the video here for further emphasis. So I'll see you in the next video for the next example.